is a Bachelor of Science Honours degree in Chemistry with first class from the University of Sri Jawatanapura in 2009. And then he obtained his master's degree in Chemical and Process Engineering from the University of Moratuwa in 2011. And he pursued his higher studies at the University of Cambridge, United Kingdom, and obtained his PhD in 2017. And he joined the National University System in Sri Lanka in the same year. And at present, he's a professor attached to the Department of Chemical and Process Engineering at the Faculty of Engineering, University of Peradeniya. He has been, from the beginning, he has been an outstanding researcher. And in 2022, he secured a research fellowship from the Massachusetts Institute of Technology, or the MIT, USA. And at present also, he has been a visiting assistant professor there in the Department of Chemical Engineering, MIT, USA. And to his name, he has authored and co-authored over 100 publications, which were presented at various world-renowned forums, and securing an H-index of 22. He has been one of the founder scientists at the Sri Lanka Institute of Nanotechnology when it was formed back in 2009. To his name, he has contributed to 3 books and more than 35 book chapters in nanotechnology and related areas, which were published by leading publishers in the world like Elsevier, Springer, Wiley & Sons, Taylor & Francis, etc. And he has received numerous international and national awards, including the CBCT Excellence Award for Most Outstanding Young Researcher in the Field of Engineering in the year 2022, Adams Glinsman Research Awards from the University of Cambridge, National Science Foundation and Technology Award, and then President's Award for Scientific Publications from the National Research Council, and the Research Excellence Award from the University of Peradeniya. So he has received all these awards at his young age. Professor Adassooriya has diverse research interests, which includes nanocomposites for agricultural applications, organic nanocrystals, mechanochemistry, and crystal engineering. So he's one of the few persons to talk about nanomaterials in this country, and it is my great pleasure to invite him to start his delivering his speech to this audience. Thank you very much. Slides at the side.
I can use the arrows, right? Right. So good afternoon, everyone, and thank you very much for the kind introduction, Dean Sir, Professor Lilantha Samaranayaka. And also I'm really grateful for inviting me to deliver a speech under this the theme under Diamond Jubilee lecture series. And today, 30 to 40 minutes time, I will dive into the topic materials innovation, and basically we will be focusing about how we use material innovation as the foundation for the advancement of science. So so this is how I have structured the presentation. So the first part, I will give you kind of an introduction, and in general, materials innovation and role of nanotechnology. And then I will pick, set off, the subsections or the fields to discuss. Thank you. So I'll discuss some selected fields. The topic is really vast, massive topic, but I'll pick some, the themes like nano-fertilizers, nano-dielectrics, nano-food packaging, and water purification technology, especially aligning with my own research activities at the department, at the faculty. And the latter part, I'll discuss how we disseminate knowledge based on our research findings there at Peradeniya. And as introductions given, I'm from Chemical and Process Engineering Department, and this is my research group. So most of the all the time I get like couple of the research assistants and a couple of PG students, and of course project students. And in addition to that, always we welcome visiting scholars. Even at the moment, we are having a couple of visiting scholars even from abroad. So my research focus is nanomaterials, nanocomposites for agriculture, energy, and crystal engineering, or nanocrystals. All right. So from the beginning, or the beginning of the humankind's, so we have been using materials for various applications, and always we are seeking the better materials for various applications, right? So, and early ages, we or the humankind use the wood base or the stone, the tools made out of wood, stones, like the at primary level. And with time, the metals were discovered. So the discovery of metal was a turning point. So in the first place, copper were discovered, and then since then, all of a sudden, the humankind start to use metals for various tools and the other applications. And nowadays we are using like over 20,000 different types of the steel for various applications. And apparently we started to use the composite materials in recent time, and currently we are using nanomaterials for various applications. Even if we look at how these the major tech era was defined, basically it is also based on materials. You see Stone Age, Bronze Age, Iron Age, Composite Age, and then Composite Materials Age, and nano materials as well. So that emphasize the importance given for material innovation throughout the timeline. And of course, not limiting to the traditional materials. Now we have modern materials, especially you might have heard about layered materials. So layered materials, of course, I'll be talking a little bit about graphene. So in addition to graphene, there are different like molybdenum, sulfide, and different other semiconducting materials. So we will be discussing about modern materials, not limiting to ceramics, polymers, or the plastics, and the other, the common engineering materials. Right. So since I mentioned about layered materials, I'm happy to talk about a little bit about graphene. So graphene, so basically it is called as 21st century wonder material. So the reason, so this particular material, of course, before I step into the properties, I'll give kind of a brief idea about the structure. So graphene, basically we all are familiar with graphite. Graphite is a layered structure. So if you peel out, the one layer from graphite, you get two-dimensional material called graphene. And you are having carbon atoms fused together like a honeycomb structure. And you see here in this SCM TEM, transmission electron microscopy, is a really, really thin material, right? Like the thickness around 100, thickness around 1 nanometer. So what is the beauty or the why this, the material attracted great interest among scientific community? The reason is, so single material possesses various properties like you see here, right? So these graphene layers are flexible and they are having transparent properties, and also you can use in various applications such as battery. Sorry. Yeah, sorry. So, so you can use various applications like due to their unique properties, and it's really lighter material, and also if you consider the strength, it is 200 times better than steel. So normally you will not get such a material with such a diverse properties in one basket. So that is why it is really, really unique material. And 2010, the discovery of graphene won the Nobel Prize from Manchester University. And also most of those discoveries are accidental, right? So since we have very limited time, I will not go in detail, but the discovery of there's an interesting story for the discovery of graphene. Like, they use Scotch tape to clean graphite, and then apparently they notice like single layer graphene on top of those, the tapes. So that's how they came up with graphene. And currently it's almost 500 million US dollar business at the moment, graphene revenue last year. But you might wondering, so the graphene was discovered 2010, now it is 2015. So are we happy with the, the advancement we are experienced right now? So there were some bottlenecks as well. I'm very happy to discuss a bit about bottlenecks with graphene because, it is not been discussed in any forum. I mean, of course, it is a brilliant material and you can attract a lot of funding, and you will find like whole institutions worldwide dedicated for graphene, and they absorb 100 200 PhD students annually. So one of the key reason, one of the key, the one of the main bottleneck where people or the scientists or the researchers stuck in the groove is they could not achieve high purity graphene for electronic applications. That was the bottleneck. But recent time, last 5 years, if you look back, some companies like, there are like numerous, the 20, 30 major giants, right? The giant companies around the world who are into graphene. So now they have their, the in-house technologies to come up with, the pure graphene, because this is a two-dimensional, like 1 nanometer thickness, very thin material. So definitely, like if there are impurities in the system, it drastically affect to the performances. So that was the bottleneck. But nowadays we find several companies like, they produce, the high quality graphene. Of course, we can relate it to a Sri Lankan context as well. We are having high purity vein graphite, right? So, and also there are different techniques available to synthesize, to manufacture graphene, like electrochemical based methods and the sonochemical and traditional, the chemical methods. But at the moment, I think in my perspective, my point of view, so we have noticed that there were, some sort of incubation time to achieve, so we had extremely high hopes, but we were stuck in the groove for some time. But now we see, the globally several companies, they are producing high quality graphene, and now it's stepping into the fields like electronics. Of course, even previous, the last decade, graphene was using for other applications like, flexible materials, and even in construction field, there are plenty of, the applications like, you can improve, there are tensile properties like material mechanical properties using graphene like materials, right? So we just had a kind of an idea about this brilliant material. So I just wanted to step into the nanotechnology area as well. So when it comes to nanotechnology, even it is same, because like couple of decades ago, the term nano or the nanotechnology was the buzzword. I mean, everyone was talking about nanotechnology, and pretty much like same scenario what we have with AI right now. And you might be wondering whether, it is no longer, in action, but that is not the case. I mean, I will show you plenty of example where we all are experiencing nanotechnology, but it is sort of a normalized situation now. So this is one of the brilliant example, because, so I took this example when it comes to, to talk about nanotechnology with public, forum, because we all are experiencing, the how our mobile phone evolved, right, with time, right? Fortunately or unfortunately, we did not have mobile phones when we were schooling and when we were at university. But now, right, even kids having access to mobile phone, you see things, getting smaller and faster and stronger thanks to nanotechnology. And this, the claim was made in 2017, 8 years back. You see, Intel, they could pack 100 millions of transistors in 1 millimeter square meter, right? So they could fabricate, in clean room conditions, right? They could go up to that much amount of, it's a massive number, 100 millions. So basically, the technology behind it is they fabricate nanoscale transistors, right? Even at that time, they were working with 100 nanometer scale, and they were putting their effort to go beyond 100 nanometer, below 100 nanometer, right? So this is one main reason, right, to miniaturizing or getting things smaller using nanotechnology applications. And of course, if I take another example from aerospace materials, of course, the aerospace or the flyings, and these days is a hot topic, right? We are really worrying about, the standards, their quality, and the etc. So you see here, so this is how the aerospace materials evolve. You see, so initially they started with metal-based system, but gradually they were stepping into composites. So in composites, of course, you can combine different materials together and come up with lighter, but whole the point of when it comes to aerospace materials, you need to have materials with higher strength, but it should be lighter. So now they are heading towards composites, using different nano composites as well. And then you can reduce fuel, the usage drastically, 20% up to 20%. So you see here, so if we use, the modern, we blend, the modern technology with, our applications, the day-to-day life application, we can, achieve a lot. There are plenty of examples, and of course, not limited to those areas. Construction field also, they are using a lot of nanofillers, right, in order to achieve, the enhanced properties. Right. So it is sort of a cycle. I mean, and also it's a very live process. I mean, always we try to come up with, the materials with higher performances. So then we do, pump money for R&D activities, and then we create new knowledge, and based on that, the new knowledge we create, we come up with, the novel innovations, and apparently the scientific, the industry can make money. It's a sort of a cycle. And since I talk about the beauty of nanomaterials and the applications, you see, if you just type nano, the term nano, you will get millions of hits. You see 400, almost 500 millions hits on Google. And this is how the revenue, right? It's almost $300 billion revenue. So as I mentioned earlier, so it is very difficult to find a single field which not has been touched by nanotechnology. Any field, basically, we are experiencing nanotechnology and the brilliant properties of nanomaterials. So if I talk about a little bit fundamentals, right? So what is what are nanomaterials? How they behave differently? The fundamental questions. Basically, nanotechnology is a sort of a revolutionary way of looking at materials, right? So my nanotechnology, science and engineering at the nano scale, which is about 1 to 100 nanometer. So in order to get a kind of an idea about what is mean by a nanometer, it is like a string of 3 atoms, extremely small. And you can see here how relatively to get an idea. So this is human hair. So those are nanofibers, how small it is, right? So of course, when we talk about nanotechnology, we should mention this great scientist, Richard Feynman, who won Nobel Prize in physics in 1965. So he delivered an interesting talk about there are plenty of room at the bottom where he introduced conceptually where you can write whole Britannica encyclopedia on a pinhead. So at that time it was pretty like a joke, because in 1965 we did not have any technology to visualize nano scale. But the point that the visualizing techniques like electron microscopy, atomic force microscopy, STM like technique discovered, people tend to believe, people or the scientific community tend to have a faith on nanotechnology, because they could see the nanomaterials by their naked eye with the support of the advanced nano visualizing technologies, right? So then a fundamental question, right? Though many people or the scientific community are into nanotechnology, so this fundamental question, I believe, is the question, right, when it comes to a nanomaterial, why they behave differently. Why nanomaterials are different compared to their bulk counterpart. So there are two fundamental reasons. The first one is they're having extremely high surface area. You see here, if you go down below 100 nanometers, so you see their size below 100 nanometer, their surface area to volume ratio or the aspect ratio extremely high. But apart from that, there's another topic, another concern, the factor which greatly affect to their properties, brilliant properties, which is called quantum confinement. Quantum confinement means because you are in extremely high, extremely small size. So when you go down, right, so their band gap or the energy band gap changes. You see, so this is, if this is the band gap for the bulk material, so when you change the particle size, you can tune the band gap. So that is, normally that topic is not in the discussion, but that property, because otherwise, as I mentioned earlier in the previous slide, somebody can ask why 100, why 1 to 100. So that regime is determined by these two factors, extremely high surface area to volume ratio, the other one quantum confinement. So that is why when you change the size, even you can have different colors, different properties. You see here, if you take gold nanoparticle, right? If the particle size is 6 nanometer, you get ruby color. But if it is 2 nanometer, you get blue in color. The reason is due to the quantum effects. I can explain what quantum effect is. But basically, they are extremely high, small particles, and then they have like pretty much like electron-like, the behavior. Right? They're having a compatibility when it comes to the motion of the electrons. So we can explain their behavior using electron gas theory. So then because of those properties, so they tend to, change their band structure. So those are the two main reasons why we have, the enhanced properties at nanoscale. And nanotechnology is not new, and it was there from the beginning of time. You see, Mother Nature knows the most, the stable way of fabricating materials. So what we do is we mimic, the Mother Nature and try to come up with our own materials. But sometimes they are high energy state and they are not stable. So that's why we are struggling, right? So, and this is very common example, even high school students, grade 6 students, are well aware, the lotus effect. So you can transform, the lotus effect where you have, the nanoscale fabrication. Here you can see there nano filaments. are there, so they can, tune. So with the presence of nanoscale, the protrusions or the filaments, so they can play with the contact angle or the contact angle of water, right? Nearly 180. So that is what scientists mimic when it comes to smart fabrics, right? And of course, most of the cases you see in butterfly wings, you get nano pouches. So that is basically, the fundamentals for nanophotonics screens. And here also you see, you get nanoscale. So that's how, the gecko can walk upside down. The reason is they're having nano protrusions, right? So then they can balance their, the weight with the reaction you have on wall, right? So yeah, even our DNA, we all are made up, we all are nano machines, right? Our DNA, 1 nanometer, right, in thickness. And our neurons, some filaments are in the nanoscale, nanoscale. That is why, those nano, the developments or the fabrications give brilliant, the efficiency, right? So we are having very limited time. So, and of course, not limiting to the, the recent time, the nanotechnology based advancement, even, Roman era, you see like ancient time, they have knowingly or unknowingly, they have fabricated nanoscale materials, right? The ruby color from nano gold, right? And you see, and even wood steel, so they use nanoscale carbon nanotubes, right? So these, materials, you see, even you can cut, hair, and also a bullet, right? It is having that strength or the strain range, right? Right. So now I just, from up to now, I gave you all kind of an idea about, the materials in different fields, and also the role of nanomaterials in different applications. So now I'm going to divert my, the talk into what we are really doing at Peradeniya and different areas. So how, I mean, our contribution and how we are pushing boundaries, right, using these technologies. So it goes back to 2009. So 2009, we started the nano fertilizer project and being part of, Slintech, the very first, the research team. And even Professor Lilantha, our Dean of the Faculty, was there, with us at that time. This is 2009. I was just, after my, the first degree, bachelor's, and I guess Professor Lilantha was just a couple of years after his PhD. And we had a brilliant team and we worked hard together. And if I explain a little bit how we transform, nano base, the materials into this particular application. And this is this nano composites application or the formulation for nano-fertilizers. So you all know that we are using urea as a nitrogen supplier. So one of the key problems with urea is they are highly soluble, and if you administered urea, flush out quickly and ended up in water bodies, and the causing eutrophication and other environmental factors, and also more importantly, the economic loss. So we are losing 40%. And so our challenge was to come up with a novel system to address this issue using nanotechnology. So here, so what we did was we used a nanoparticle, hydroxyapatite nanoparticle, and hydroxyapatite nanoparticle itself is a fertilizer because it contains phosphorus. And then we anchored urea molecule on, because already I mentioned that nanoparticle having extremely high surface area. So then you can load, the urea molecules on top of the nanoparticle, hydroxyapatite nanoparticle. And for the safe side, because, our target was to, the tune, there are kinetics, release kinetics. So then for the safe side, we embedded this nano system or encapsulate with a nano clay. And also we tried to encapsulate in the plant material as well. Right. So this is the point where we wanted to get support from Professor Lilantha, because we wanted to come up with a pressure chamber to pressurize these nanos, dispersion, to get them trapped in, the xylem vessel of those, of course, Gliricidia itself is a fertilizer. So we wanted to trap those nanonutrients within that system. So this is the team, Professor Nirala and Professor Ima. So all our professors now. So we started, as graduate students, and you see here, so we could reduce 25 to 50% reduction of fertilizer application, and of course we could improve the crop yields 10 to 15%. And apparently even the project project continued even though we left the place for our doctoral studies, and even they commissioned a reactor to produce these system in bulk. And then here we could achieve 2 US patents, and these 2 patents actually are, so this is some images from this project, and even as I mentioned earlier, we could file 2 US patents at that time, and one of those holds the record of first US patent, nanotechnology based US patent from Sri Lanka, and the institute could transfer the knowledge to one of the leading Indian fertilizer company, and apparently the country could earn $3 million as well, right? And so that's how we started. So we transform our, the nanotechnology knowledge into a tangible product. And of course, this is one example out of many. So that, explain how we can transform advanced material developments into the many fields, different fields, such as agriculture. And of course, our effort was, the well recognized at National Science and Technology Awards. And yes, so that's how we started the nanotechnology based, agricultural applications. And then the story continues. Then I joined with Peradeniya. Actually, I joined permanently with Peradeniya 2020, but I was working with Peradeniya since 2017. So then we started another, we wanted to push forward the same project. And then so we applied another phenomena, or the concept where I experience in pharma industry, so which is called co-crystal based nanofertilizers. So this was new to the field, and our research group published the very first paper, right? So using these concepts where to tune the urea release. So in this concept, what we did was, so we use urea and use another third-party material, and we ground these 2 materials together. It's a solid-state reaction to come up with a solid-state novel material. So here, in the presence of very minute amount of liquid, which act as a having a catalytic activity. So then it's a solid-state reaction, so no solvent involved. It's a green synthesis. And so then you can even convert them into nanoscale. And then we carry out same set of, the experiments and at lab scale and pot trials and the field trials. And then we came up with a novel, the fertilizer. We open up this novel fertilizer material to the field. And then from that point onwards, the many research groups around the world are working on that same front. So this is the first paper, a pioneering paper we published in 2022 in a really good high impact journal. And then Royal Society invited us to write the highlight about that same topic, because they wanted to popularize the same idea with the scientific community. And so at the moment, we are progressing really well, and we are doing, the plant trials with different crop species, how it behave. And also we could file a Sri Lankan patent as well last year. And yeah, so this is how we push the boundary, starting with the nano fertilizers project at Slingtech, and then we open up a new field for scientific community to work with. And not limiting to that, so we wanted to study further about nano conversions. So, converting them into nanoscale is always is a challenge, because we are at solid state and we want to convert without using any solvents, because we wanted to focus on green synthesis approaches, less solvents involved, and then only when it comes to the scale up, our life will be easy. So then luckily I was very fortunate to step into MIT, and there what we initiated was we studied how to convert those, macro size materials into nanoscale using different nano crystallization techniques. So they are basically, I carry out some projects about how you get nano crystals in confinement or the confined area system or a matrix. And still we are continuing. Even recently also we collaboratively published one paper with MIT, and it opened up our students to get exposed to researchers from high-end places like MIT and Cambridge. Right. So there are some more example, and this is back to the first pharmaceutical materials, and also we are working on pharmaceutical materials as well. We are trying to, so in pharma materials, so we can improve their properties. When it comes to pharma materials, release kinetics and their dissolution rates plays a very important role, right? So we can have, the solid state pharma materials, sometimes they do not dissolve properly, and even, I mean, you administer orally, let's say orally, as tablets, and then sometime, throughout, your body, you will not have enough time to get absorbed, the active ingredients to your body. So then you need to tune their kinetics. So that is one aspect we are focusing on. And globally also, in global context also, we have realized that there's a huge vacuum. Big pharma giants want to convert their, the pharma materials into nanoscale and come up with, nanoparticle or nanocrystal, containing tablets to tune their kinetics. Right? There's a huge vacuum in scientific landscape, right? Right. So at Peradeniya, we try our best with our limited facilities, to convert pharma bulk materials also to nanoscale. So there are several projects going on, nano aspirin project and nano caffeine project. So we try to convert them using solid state. You see here, so this is bulk material. So then you use different types of techniques, like maybe grinding, using vibratory mills and different types of milling techniques to convert them into nano and see their physicochemical properties. And also we are working on nutraceuticals as well, food supplements, because, since we are working with pharma materials, so very easily we can step into pharma, in the nutraceutical as well. So then we try to, entrap different types of, the nutraceutical or the food supplement. That most of the food supplements are from biology, and they are really fragile. I mean, we extract them from plants, and once we extract, with time they degrade. So we want to stabilize them. So then what we do is we use different nanomatrices to stabilize them, and then we go through the whole spectrum. We study how they release into the medium and their lives, the lifespan and shelf life, everything. Right? And of course, several times our studies, our findings were well recognized at different forums. And this is another field that I should talk about a little bit about, energy storage as well, because it is my PhD area, PhD field, energy storage devices, materials for energy storage. Since we are actively engaged in pharma and agriculture nanocrystal, because it's a very niche area where we can contribute, and there's a void in that area. So in Peradeniya, so we try our best to, to explore that area, since we are having facilities. And of course, energy is challenging. So we were doing nanoscale devices. So here, basically, materials for energy storage. You see what basically we did, and we did a couple of projects as well here at Peradeniya. So basically, if I brief about this project quickly, so our target is to come up with novel materials to store energy. Basically, the whole the objective is to come up with novel materials with higher energy density, and at the same time we are focusing about power density as well. So here my focus was to embed nanoparticles, different nanoparticles in different dielectric, the thin films, and see the energy storage capacity. So that was my whole PhD project, right? But the beauty is this whole system is 300 nanometer in thickness. Even you cannot see the device by your naked eye. So it is on a silicon wafer, and then you fabricate your first layer, right? Aluminum electrode like 100 nanometer in thickness, and then this is your nanocomposite. So you have your polymers, and you embed your nanoparticle in it, and then your top or bottom or the top electrodes, same aluminum electrode, 100 nanometer thickness. And then you measure all the electrical properties, probe measurements, and see how it behaves, right? And so luckily there we have all the facilities to fabricate, the nanoscale devices, and then you can see their electrical properties, their the dielectric properties and leakage currents. And also you see this is AFM image, how small, in terms of thickness, you see is less than even 100 nanometer. So those are the dielectric thin films. And you see like you can have those nanoparticles embedded within the system, and you can see how charge dissipates even, for any material there is at least, the nanoscale, picoscale leakage current. So you can even trace out those leakage patterns as well. So that was my PhD project, and this was funded by Dyson at Cambridge University Engineering Department. So, so this is another, interesting area. Of course, right? The energy is one of the hot area, right? So we are scientists trying to push boundary. It may be battery research, it may be the solid state devices like dielectric capacitors, etc. So there's a huge demand still. We try our best to come up with the high energy density materials. So you can sometimes achieve high energy density materials, but still sometime in you may have like extremely high leakage currents. So then you have to compromise energy density and the leakage. You have to have a sort of a balanced situation. So this is simply, I took that example to give you kind of an idea about how we can push, energy sector, especially the energy storage area, using advanced materials. Right. So back to another topic, a completely different area. You see, this is the beauty of nanotechnology. Like nanotechnology, I would say, is the most multidisciplinary platform ever we had, because you can you are tuning material properties using nanoscale materials, and so you can step into any fields. Basically, you fabricate the material. It can be energy, it can be environmental engineering, it can be pharmaceutical, it can be food sciences. Whatever the field you can step into, because basically you are tuning the properties at nanoscale, and then you come up with new materials. Right, so this is one of our own project at Peradeniya, funded by URC, University Research Council. And here, what basically we are trying to do is to come up with a system, nano adsorbate based clay pot for water purification. So this pot is made out of, using, non-toxic nanomaterial. Always, since I'm into nanotechnology or nanomaterial, always I make sure that I'm using user-friendly materials. Otherwise, there's no point. It can be a brilliant innovation or a discovery, but still it is not practical. At the end of the day, no point, right? So here, so we are using nano clay and, very common nano clay MNT, and of course we need to have a natural clay to come up with the the pot itself. And of course we are using TiO2 like grass, the chemicals where even you can use for food formulations. So here we got really good properties. with this system. And at the moment, we are in the process of, filing a patent. So here, why I took this example, irrespectively the field. So if you use, the material, if you tune materials, you can apply it into any field, right? And so this is another example. We are working on food packaging materials as well. So packaging is another, challenging field because we have been using synthetic polymers, and polymer was a brilliant engineering material, right? If you consider like 3-4 decades now, we are having, drastic, the issues with polymers. Catastrophic situations, so we have huge non-degradable plastic deposits here and there. Even we have 5, the major deposits in the sea. The one nearby California is even visible to outer space now. It is like 30 times bigger than our country. You see, it's fully covered. Those are plastic forests. And that is why will trend towards biodegradable polymer based materials. So we try our best to contribute in our capacity to come up with novel biodegradable polymer nanocomposites for packaging applications. So you see here also we use different clay systems and embed them in biodegradable polymers, because one of the key challenge when it comes to biodegradable polymer is they do not have enough strength. And also, since they are degradable, so that means they have, the exposed functional groups. So those functional groups interact with water outside. So because of that, they tend to absorb moisture. So then you lose the strength, right? And apparently they become soggy. So those are the challenges that we have to, to address as material scientists. So here we incorporate different nanofillers. You see, this is a TM image, nanopart platelet embedded in a polymer matrix, to improve their reinforcement or the mechanical properties, and at the same time barrier properties. So we wanted to cut down, the moisture get into the system, right? And I already mentioned about graphene. So we are also contributing to graphene research as well in our capacity. So this is one of our MSc research project. So that student basically use a concept where you have in Pelton bucket in hydro, the system that. So then he mimic the same, the system, get that force to break down in the nanoflakes or the graphite into nanoflakes, right? And we could achieve, the nano or the single, not exactly single, at least few layer graphene platelets using this technique. And here also we file a patent, and at the moment this student having his own startup company to have our own graphene from our own vein graphite. Right, so I'm reaching to the latter part of the talk, and this is more projects like how we advance. We try to improve material properties for various applications. So we are working on bone grafting materials as well, and also we are focusing on nanocrystals using sonication, because always we try to utilize green methods. So then so when we talk to industry, so if you use the tons of different chemicals or the solvents, they are very reluctant to come forward. But if you use mechanical methods and the sonochemical like methods, they are pretty happy to collaborate with us, right? Because basically the cost factor matters a lot. And also not limiting to the applied research, we are focusing on fundamental research as well. You see the heat exchange capacity with different nanofluids. So there's one project going on. We are trying to improve the heat exchange capacity using different types of novel nanofluids. Right. So simply what I did was, so I try my best to give a kind of an overview about how we utilize materials innovation right, for the advancement of science. And also I took this opportunity to showcase our own research activities as well, where we are doing at Peradeniya. And luckily we are having really good, healthy collaborations with world top places. And of course, Cambridge is supporting me from the day one since 2011. We have very close relationship with Cambridge University, and after joining with MIT, so we have a couple of the collaborative projects on pharma crystals, nano crystals, and of course I do collaborate with a couple of Indian universities as well, where I have my colleagues as professors there, and even SLIT and Java Dinapura Slim. So we are very blessed to have the healthy research collaborations that really help me to push the boundary and to do something new at Peradeniya. And of course, so these, as I repeatedly mentioned, our effort was recognized at different the occasions. These are a couple of the university from University of Peradeniya and CVCD Research Excellence Awards as well. So, and also I would mention the financial support we received from National Research Council and AHEAD project, Peradeniya, and multidisciplinary research grant, and of course, University of Peradeniya research grants as well. And we did not stop, just publishing papers, and we wanted to push the boundary further, and have contributed so many books with the different editors. But this year, so one of our key, the book will come to the audience or the community. So still it is under the production stage. So I could get down people from various high-end the institution to edit this book, industrial scale production of nanoparticles, because as I mentioned earlier, there are bottlenecks when it comes to the nanoparticle productions, right? I mentioned about graphene and why the scientific community is stuck in the groove for some time. So we wanted to emphasize on those challenges we have and how to overcome. Especially we wanted to focus on scaling up aspects, right? So this is one of the recent delivery from my research group with the support of two eminent the researchers, one from previous the past staff member from my department, and another one from another country. So we continue disseminating knowledge to the other, to future generations as well, not limiting to our research activities and filing patents and publishing papers. Right, basically that's all I wanted to deliver today. Basically, I wanted to give a sort of an insight about how we use the material advancement in material sciences, materials engineering for various application to improve the technologies and in various fields, not limiting to one field. So that is the beauty of nanotechnology, because it's as I repeatedly mentioned, the most interdisciplinary platform ever we have. And thank you very much for your attention, and if you have any questions, I'm very happy to take. Thank you.
Yes, thank you very much, Professor Nadeesh. So it was actually a thought-provoking and insightful session for us. And so this is now for the audience who are presented here in the auditorium, and then the ones who are present online. So you can ask your questions if you have any, and we can send it to the Professor Nadeesh.
Of course, that involves a lot of equipment. So, what is the cost of the equipment? So, I mean, when we should see something like we understand commercialization is of and we need the factory Yeah, we need the equipment, so we have certain areas we have set up.
Yeah.
Especially when it goes to the nano area, the area, right, what is the normal thing?
Yeah,
You understand what I said?
clearly I got your point. And yes, with the experience that we received from early stages, because we were working with the industry that soon after our, the bachelors, and we got to attend, meetings with industry people face to face, and then we got a sort of a sense about what they really expect from us. So I was in that track from the beginning, right? So I'm fully agree that, so that is why even during the talk I mentioned that always we stick to, the first point is always we stick to, the green materials. So that was one, the main concern. I mean, so we are using nano clays and basically we call grass molecules, like, generally accepted as safe molecules. When it comes to scaling up, of course, as I mentioned, always we focus about some green, the manufacturing technologies. Always I'm pretty much into the top-down approaches like milling techniques. So we do a lot of, the experiments, like we want to get rid of solvents. So then when it comes to say scale up, life is easy because you are not using then no downstream, the processing, and you are not using solvents, and cost wise it is, really beneficial. And at the same time, when it comes to, the technologies or the instrumentation, of course, so if you focus on same example, milling techniques, you simply want to have, the mills or the, I mean, the one of the, the concern with general public and people who are not, the seriously into nanotechnology, they think that you need very specific, the apparatus and manufacturing methods to come up with nano materials. But yes, for nano devices, I completely agree with nano devices. But even at our laboratories, at my department, we can synthesize nanomaterials in kilograms. So you simply want to play with flow rates, and you need to have some agitators, and then you can come up with the relatively pilot scale production. So I strongly believe that strongly believe that if you pick correct technologies or the methods, techniques, definitely you can overcome those barriers. I mean, you go for solvent-free methods and techniques like milling techniques, grinding, top-down approaches, and then definitely you can get rid of all the bottlenecks. That's my idea. Since we had that experience in the beginning, so all my projects we are focusing on milling-based techniques and green nanomaterials, because otherwise you can have brilliant, the findings, but no point like when you discuss in front of, people from industry. I mean, you can't maintain the same credential what you have, in publishing your work in different forums. So we are really focusing on that lines. So. Yeah. Yeah, you transform nature into application, you mean. Yes, we have. Right. So we have, especially like we were in like projects like nano fabrics, like, so that's a very, approachable technology here. So always you see, like, what comes first. I mean, I did not focus on nano devices here. I mean, even I had, several discussions even with our the dean as well. So I wanted to do some nano device fabrication, and still I believe that we do not have enough facilities here in the country to devise nanoscale devices. So yes, so nano fabric is I mean one area that we can easily work with. Even we have done some work, and I know that several Sri Lankan companies where they do have nano fabric based patents as well. And so there you can basically modify nano fabric surfaces and come up with brilliant properties, smart fabrics and wearable electronics, etc., etc. But not in particular that so I realized that my niche area is nanocrystal. I mean, there's a huge vacuum in even in top 10 places. Still, still they are also in in the very beginning or starting stages. I mean, they wanted to come up with strategies, in-house strategies to come up with organic nanocrystals. So then I'm focusing on that line. But yes, I mean, so we have to figure it out, what are the the system or the material development doable in this system in our context, and then we move on. So we have been very practical, to be honest, with the limited facilities we have, but we did not want to give up it. So we try our best to to do something new and contribute to the community. And of course, I strongly believe that we should not stop at the ground level or the bench level. So we should push our boundaries to the other side as well. Yes, sir.
AI was not. You said that nano was very popular, like AI.
Yeah.
Is the impact for the research in the AI because of the AI? I don't.
Yeah. Yeah. Because of course I'm not an AI expert, but anyway, I believe that I believe that we should expose to AI as well to see whether to get whatever the benefits from AI into our field as well. Of course, I'm pretty sure that there will be loads of application in nano, because when it comes to material selection, and when it comes to, because we can use those the data driven models and the AI based the systems to for example, like if when it comes to nanomaterial synthesis, if you can narrow down the different options we have with the support of AI, it's a great support. I mean, so then you don't want to try out 100 different types of the manufacturing or synthesis methods, and then you can narrow it down into a couple of systems, and then you can execute the experimental activities in laboratory. So of course, I strongly believe that AI greatly will influence nanotechnology and material science as well. But I'm not an expert. Of course, we should dive into nano, but at the moment we are focusing on more into generative AI. But I think it's high time for us to focus on nano and the AI interface as well. Thank you. Yeah, they're having, yeah. Yes, yeah. Actually, recently we completed that project. I mean, we are at the latter part. So this is purely from our department, Peradeniya. Yeah. Yeah, yeah. Yes. Yeah. So our target was to come up with very simple apparatus. I mean, we didn't want to go for nano filters. So we wanted to target domestic applications, especially in rural areas. So then, what we did was, yes, I mean, our project was influenced by the idea that so Madam put forward. So, we have been using those, the clay pots for, even to store water and, so then what we wanted was to go like one step beyond, and then we embedded different types of nanofiller in it. And then we could, get rid of, for example, microbial contaminants is very common, like, especially, in rural areas and some, different, I would say, setups, right? Sometimes you get more, the E. coli contaminations in some setups. So then we wanted to reduce. Yeah, even we tried for heavy metals as well, because, we are having a very smooth nano surface, so then they are happily absorb things. So then even we noticed that we tried for different types of heavy metals plus microbes. So we have good numbers, of course. So then we are in the process of filing it. Yeah. Yeah, of course. So yeah, so then I think even we could reduce the E. coli up to 80%. 80%, and there are really good numbers for the heavy metals as well. So we carried out whole spectra to see the efficiency. Actually, at the moment, yes, we did not, because recently we completed that project. So we will extend it up to a certain level as well. We are having some plans. Yes, fluoride is another very important, the contaminants, and northern part of the country greatly suffering from the high fluoride content in water. So definitely we will focus on fluoride as well. But we did some projects for fluoride as well using layered methods. We got good data. Sure.
So we got a question from Dr. Nawaz. So the question is, in civil engineering, especially in geotechnical and structural applications, we often deal with materials like concrete, asphalt, and natural soils. How can recent advancements in engineering nanomaterials such as nanosilica, carbon nanotubes, or graphene be realistically integrated into large-scale infrastructure projects to enhance mechanical properties or durability?
Yeah. Recent advancement. Yes. Yeah, so as you clearly mentioned, in the question, so of course, there's a huge influence from nanotechnology to the field of construction and the civil engineering related fields. So as you clearly mentioned, researchers trying to get, those reinforcement materials like graphene and carbon nanotubes and the other nanofillers into concrete to improve their strength and the other properties, water permeation even, like you can control, if you use, layered materials, even you can control water permeation. And the beauty of, such applications, since in my introduction, I mentioned that nanomaterials having extremely high surface area. So you can achieve, the required desired properties just applying very minute amount of material. So that immensely contributed to the sustainability aspects as well. So that's one, the important property when it comes to nanomaterial. So you can achieve the same property. Otherwise, if you use, tons of carbon nanotubes or graphene in construction, of course, that won't be practical. So then you want to fine tune their properties, and of course, due to the brilliant properties of nanomaterial enables to use, very low loading to achieve, the desired properties from construction materials. Even I have seen, since I'm not into construction field, construction materials, but I have read and I have seen that, there are plenty of applications, and even in industrial scale, they use nanofillers to get, desired properties. So I emphasize the point that you can achieve those desired properties using very small amount of material. So that's the beauty of nanotechnology. Of course, it is possible to get those enhanced properties with the introduction of nanofillers. Thank you. I don't know whether I give the answer, but I noticed that so because answer itself was there in the question, because so those are the recent advancement when it comes to the construction materials plus nanotechnology, employing different nanofillers. So civil engineers in collaboration with the material science and engineering, the people who are into those fields, so you can come up with novel materials, fine tuning, their desired properties to come up with novel materials. Thank you.
Yes, so thank you very much. And I think to conclude today's event and session and to formally deliver the word of thanks, I now invite Ms. Yashoda Vimukti, the lecturer at the Department of Computer Engineering, University of Peradeniya. Over to you.
Thank you. Good evening, everyone. It is my great honor and privilege to deliver the vote of thanks at the conclusion of today's insightful session of the Diamond Jubilee Lecture Series organized by the Faculty of Engineering, University of Peradeniya. First and foremost, our heartfelt gratitude goes to Professor Nadeesh M. Adassooriya for delivering a truly inspiring lecture on materials innovations, the foundation for the advancement of technology. Your deep insights into the critical role of material science in shaping the future of technology have enriched all of us and resulted meaningful reflections on the direction of engineering research and innovation. Special thanks goes to the Dean of Faculty of Engineering, Professor Lanka, for his unwavering support in organizing this prestigious lecture series. His leadership and commitment have been instrumental in making the series a success. We are also deeply thankful to the Institution of Engineers Sri Lanka, IESR, for hosting us at the Vimalasurendra's Auditorium and for their continued support in facilitating this important academic collaboration. To all the eminent professionals, engineers, faculty members, students, and online participants, thank you for joining us and contributing to the spirit of learning and exchange that this series aims to foster. I also extend sincere appreciation to the organizing committee, technical team, and the volunteers whose efforts behind the scenes ensure the successful execution of today's event. Finally, thank you to each and every participant for being part of the Diamond Jubilee. We look forward to welcoming you to our future lectures as we continue to honor 75 years of engineering excellence at University of Peradeniya. Thank you and have a pleasant evening.
Thank you very much, Ms. Yashoda. So with that, so we wrap up today's inspiring session. And we are reminded once again that the journey of innovation is built on strong foundations, and material science is one such pillar. So thank you all for being a part of today's lecture, and we warmly encourage you to stay engaged throughout this special year of celebration. And don't forget to mark your calendars for Engineering X 2025 this September. Until next time, take care and good night.